In this video, we'll look at how to simulate erosions for a pneumatic systems carrying solid particles. So say we have a domain like this. This is a straight pipe with a 90-degree bend. So the floor is coming through here, and that floor is carrying solid particles, silicon carbide solid particles with a mass flow rate of 0.02117 kilogram per second. So the flow will pass through these pipes, going through this bend. So some of the particles suspended in the floor will hit these part of the pipes and causing erosions. So we will use CAD to simulate these sort of problems. But first we have to create the geometries. The geometries for you to input into your CAD software. So the geometry is, we have a pipe bend. So the bend with a curvature radius of 1.5 diameters, 1.5 times the diameters of the pipes. So the diameter of the pipe is 0.0254 meters. So this is a very simple geometries that you can easily create in your SolidWorks. So if you open out your SolidWorks, you can go to your top plan, and create sketch. So this will represent the length of your pipes. So you can create the length of the inlet of your pipe to be 20 of the diameters. 20 of the diameters will give you about 0.5 meters. So you can say this to be 0.5 meters. Then you need to do this one, the curvatures. We can use the center arc with a radius of 1.5 the diameters. So this is 90-degree bend. So this is the Y here will represent the radius of curvatures. So the radius of curvature is 1.5 diameter. That will give you 0.0381. .0381. one. This is the starting point. This is the end point. So this is the radius curvature. So this is 90 degrees. Okay, so that creates your bend with a radius curvature of 1.5 diameters. Then we can create your outlet pipe. So this is shorter, so you can make it 10 times the diameter of the pipes. That will give you about 0.25. So once done that, you can exit. And use the sweat bolts from the base. So before you actually do that, you should create the circular profile for your pipes. You create a second sketch using the right plan. So click sketch. This is happening at your base. So simply click on circle. At the center with the diameters. So the diameters would be half of 0.0254. It will be 0.0127 meters. Click exit. And now you can use the sweat bolts. This will be the sketch 2, this will be the sketch 1. Click OK, and you have your pipe geometries. So in this problem, we will look at one of the strategy how to reduce the erosions at your bend. So what we're going to do is we're going to install this particular swirler at the surface of the bend before the flow can hit, the flow reaches the bend. So now we will create the swirler. We'll create a swirler around here before the bend. And that swirler will have a length of half of the diameters of the pipes. So what you can do is you can create a plane from the surface. So now you have plane 1. So from your plane 1, you can create another plane so that you can draw, so that you can decide the locations of the swirlers. So create a second plane based on the first plane. So say you intend to put your swirler here. Okay, so that's create your plane number 2. Maybe you can hide this one. Now based on your plan number 2, you can create your swirler. So you can sketch your plane now. So it's gonna be your swirler gonna be located at the surface. Create now exit the sketch. We have this point. This point represents the bottom, actually the surface of the pipes. This is where we're going to draw your swirler. So now this is your front plane, and we can create a plane at this point using a front plane. So create a plane again and create this. So this will create a plane actually where we can draw. This allows us to draw our swirler. So sketch on plane number 3. So you might need to orient it a little bit to be like this. So you can hide your pipe as well to give a little bit of clarity. And so we're going to create your swirler that is crossing this middle point. Maybe you can create a swirler like this. So this is measuring 45 meters. So this swirler is measuring 45 meters from the angles. If we do 150, this will be a swirler that is 50 meters away from the horizontal axis. Now we're going to create your swirler with a length of 0.5, half of the diameters of your pipes. Okay, half of the diameter of the pipes. Half of the diameter of a pipe will give you 0.0127. So we create another line again. So this continue, this is the second half of your swirler. So now we have the swirler, the base of the swirler, create exit. We actually now have to sketch it, sketch the remaining of the swirler. Again, we need to create a plane for that. So we can create a plane based on this line. We can create a plane. This, so this, we have a plane now. So this is a plane number 4. Click sketch. This is your plane number 4. This is the length. Now create some line. So this part of your swirler will have 50 degrees. This means that this is gonna be 310 because it's measuring from the base, okay, base of plane 4. Now create another line. This line gonna be 25 degrees. So 360 minus 25, they will give you 225. Now we have actually these two lines that they will intersect, and you can create another line. Create another line and delete the old one. So now we have our swirler for our plane number 4. We can hide this one as well to see more clearly. Hide this line as well. So this is the swirler on plane 3 and 4. Okay. What we can do now is we can extrude. We can take this sketch and extrude it. Because your swirler gonna need a certain thickness. 0.005 or 0.001. This will be a reasonable thickness. So now we successfully created the swirler and the pipes. So we got two body. Together, what we need is the fluid. What we need in our CAD is to calculate the fluid, the domain for the fluid, which means that we need to cut out the pipe. Your main pipe, cut out this swirler from your main pipe. So what we can do here is we can use the functions called combine. So the sweet one will be the main body, and swirler would be the body to be subtract. So to do that, we can see here now there is a hollow part here. So that hollow part actually represents the space taken by the swirler. So we're ready to import this. So we can save these files and ready to import into your StarCCM. So now we will look at the CAD simulations. We will use a StarCCM to simulate these particular type of problems. And now the next stage is to set up the model in your StarCCM. So these are the standard steps in setting out CAD simulations. These are the things that we'll look at today: the boundary condition, meshings, looking at how to set up physical models, how to set up the strategy to solve the solutions, and some technique also to post-process. So you open out your StarCCM, create a new case, and import the files that you just created in your SolidWorks. So if you import it, you're able to see it in the geometry part here. What you can do now is to name the surfaces. Okay, inside StarCCM you can use a split by patch. So this actually is your wall. This is going to set the boundary conditions. You can click Shift, click Control, so I'll name for this as wall. These two as bed. This will be your outlet. This is your inlet. Now the remaining are actually your swirler. Okay, so you can just rename the remaining as swirler. Once you're done there, you need to create a new regions, create a new physics continuum as well. Double click on the model. This you have to select an appropriate model to represent your problems. We will have 3-dimensional. We're gonna simulate a pneumatic system, means that it will be gas. This will be a steady state problems that do not change with time. We're going to use couple flow. So constant density will not involve in temperatures. Gravity. Lagrangian multiphase, they will represent the solid particles inside the fluids. It's going to be a turbulent flows. We can use K omega with gamma transitions. And we will not need anything else. Okay, so if you double click your model here, so the flow is going upwards. You can consider the flow, the gravity. This represent XYZ. So if the pipe is if the flow is going upward, then we have the gravity along the x directions. So it will be minus 0.18 here. This will be 0. So that's your gravity, your air. Now this, you have to create a new phase to represent your solid particles. Okay. So go back to your model once you created your solid particles, and here you have to specify the type of the particles. It's not a gas, it's a solid. In fact, you can have drop, you can have shear force. You're gonna also need the erosions. It's a constant density, and click OK. So once you've done that, you will have a series of options here. So this, the drop coefficients being used for the particles. This is the coefficient being used for the lift force. And here you can specify the density of your solid particles. So in any case, our particle density will be 2600. So this will be 2600. And here we can specify what is happening when a particle is reaching the wall. Okay, this here we can specify to be rebound. This is the model. We will use an Oka model. And here is the coefficients, the tangential and normal coefficients for your rebound model. So In this case, we have to key in manually the rebound model. We will use a grain and Tabakov model. So grain and Tabakov model for your rebound. For the particle rebound is given by these equations. So what we can do is we have to create these two functions manually. So we can go to the tool here, go to the field functions, and create a new scalar functions. So copy these equations, paste it into the definitions. This will be the normal execution coefficients. Now create also the field functions for your tangential. So now we created the field functions. We can specify our rebound model. Here we say field functions and select the functions that we just create. So search for E normal. Then do the same for this. Search for E10. With this, we almost fully set up our model. We can even rename this one as the solid. The next thing we have to do is to specify your boundaries. So you can rename physics 1 as gas, or you can just simply rename it as fluids. Okay, so if you do that, you go to region 1, you will see you can select the physics continuum here as fluids. You can rename this one as your domain and proceed to create the boundaries. So this is the boundary conditions. You can specify your boundary conditions for your problem here. So the type of boundary condition here we can specify for your wall will be wall. You will have same name, the type will be the wall, and here you can select. So the band, the swirler, the wall, all of them have wall, and you have inlet and outlets. And create new boundaries, rename it as inlet. Select your inlet, select velocity inlet, rename this one as outlet. So select outlet, and the conditions for your outlet will be the pressure outlet. So you set up your boundary conditions. With this, you set up the boundary conditions. Now you need to specify what is the velocity. Velocity for your inlet, we are looking at 34.1. So you can specify here to be 34.1. The direction is normal to the boundaries. So you can specify your initial velocity as well. You can say that your domain has initial velocity everywhere, same as your inlet initially. Maybe you put it as 30. Now we need to create actually the inlet for your solids. So your solid particles is entering your domain through the inlet. So you need to create a new injector and maybe rename it as, you know, the solid. So select solid. It's a part injectors and it is input from your inlet. So parcel stream, this is how many parcel streams per injection point. So you can increase that one to 3. This is the mass flow rates of your solid particle going into the domains. We are looking at the mass flow rate of 0.02117. Okay, this is the amount of solid particles entering into the domain is 0.02117. 0.02117. Correct. Diameter of the particles is 182. So you change this one. You can change the unit to micron. Key in 122. Now we fully specify your solid domain as well. So next step is to create the meshings. So create new mesh for your 90 band, for your domain. You're going to use all these functions. You can use a polyhedral, you can use a thin mesh. So we're going to create the boundary layers as well. So at the start, we can use somewhat coarser mesh at 0.003. So the boundary layers, we can have 3 boundary layers. So we can use custom control here and use this to increase meshing in some of the key regions. For example, the inlet and the band and the swirler, these are the key area which will need higher density of mesh in order to capture the flow physics around all these key regions. So what we can do is we can select the regions where we will apply higher number of mesh. So we can just change this one to customs and say that it is 4 times more, so it's 25%. So the size of the mesh around these regions in your band, in your swirler, will be 4 times smaller than the mesh size that you prescribe to the rest of the domain. So once that, you can execute and see what it looks like, your mesh. Once it's done, you can go to here, the meshings. So StarCCM is automatically generates all the meshings within your domains. All you have to do is simply just to specify the kind of mesh that you want and how many meshes that you want inside your domains. So StarCCM will take care of the meshing and also the quality of the meshing. So now it's done, you can see actually your meshings. So this is the inlets, and you can see the mesh distributions within the cross-sectional area of the pipe, and also the boundary layers that is generated inside the pipes. So this is a swirler, and you can see over here we get higher density of mesh also around at the bend. Okay. So what we can do now is we can go to derived part as well and create a planes so that we can visualize the mesh inside of your pipe. So what we can do is we can specify the plane. So this is 0, this is 1. So this is a plane that is cutting through the middle of your pipes. So notice this is created. You can set it its exact plane. And you can go to scene here, create new mesh. And select your part here to be the mid plane. So you can deselect everything and select only the part for the mid plane, and you can now visualize the mesh. Okay. Inside your pipes. Right. So we're basically ready to run your simulations. And before we run, we can take a look at how to plot the erosions. So we're interested to determine the erosion at the bend here. So the question is how we can plot the erosions at here. What we can do is we can make use of the derived part as well. Go to your derived part. we will make use of the plane as well, and in this case we will select your band only. So this is only just the surface of the band you can see. See, it's just creating the surface of the band. Still, this particular derived part has the outer surface of the band and inner surface of the band, and we need to get rid of the surface at the inner band. So what we can do is we can use another function called threshold. And before we do that, we need to define actually a spherical coordinates, so that we can apply the threshold to only looking at to basically exclude out these inner band sections. So now we go to tool and create a new coordinate systems, a spherical coordinate systems. So we have to place the center to be the center of the curvatures of your band, and that value will be here. Okay, you will have the x of 0.25, and your z. So here the center of curvature is 0.0318. So now you have actually a coordinate system that is measures from this point, the center of the radius of curvature for your band. So we create this. We use this solely for creating sections for your outer surface of your band. So we go to threshold here. Again, we can select our derived part. So this is your band. Your scalar, you can go to positions and use your spherical coordinate that we just created. It will be the radius. So we're looking at here. Actually, we're looking at, so here if we specify the extraction to be above the threshold value to be 0.021, this basically we say that we only will we only look at the surface above the radius of 0.03381. So now we can see that it excludes anything that is below 0.0381. Anything it excludes everything that is below the radius of 0.0381 from the center of the curvatures. So you can rename this one as your outer band. So once you've done that one, you can go to a plot here and create a new XY plot. So you can select here your outer band. And select the scalar functions to be erosions. So you don't have anything initially. There's nothing here because you have not simulated anything. So once you simulate, you would once you finish the simulation, you would have some results here. To visualize what is going on, you can create several scene plan as well. For example, you want to see the velocity vector of the flow inside the pipes. You can go to here. You can click you can click the mid plane, so exact plan, and you should be able to see it once you have the solutions. You can create another scalar as well to show the velocity inside the pipes. So go to part, go to exact plan as well. So scalar view, choose velocity. Part, choose plan. So there's nothing here at the moment because we are not simulating anything. There's nothing here as well. Now we're ready to simulate. We can initialize our solutions. And run. So you might need to turn off, because we're doing one-way coupling between your gas and solids. We can consider turn off the solver for your Lagrangian particles and only solve it at the very last iterations. So we can do that by going to your solver and try to freeze your solver with the solver for your Lagrangian multiphase, and this could significantly improve your solution speed. So you can also divide all your sections like this. Now we have the vector plots. So you can see the changes inside the solution. This is the velocity plot, your velocity plot. So you can see how the solution changes in each iterations. We probably need to run this one for quite a while until we achieve a much smaller number of the residual. So what is output here is the residual of all the equation that you're solving. So we're solving the continuity, the momentum equations, as well as the turbulent equations. So these are the equation that we're solving. And this graph is showing the residual, is the graphical representative of all the values outputted here. And we need to solve this one to until the residual gets to reduce to a much lower value or level before we can run our Lagrangian solver to determine the erosions in your pipes. So you can see how the solutions evolve right now. So now we are at the iterations of almost 300, and we can see the residual have reduced to a significantly lower level. We can stop our solutions. So we can see here how the swirler is impacting the floors. So this is the velocity vectors. And we can see here also the velocity contour, and we can see how the velocity changes close to the swirler, and this could possibly impact the floors at the bend. So what is important now is plotting your XY plot. So now we can unfreeze the solver for Lagrangians and simulate for one-time steps. So it's done. Now we can see the erosions patterns at your bend. So what we can do is we can create a new scalar scene as well. Choose erosion rate, and looking at actually your bend. So you can go and select wall. You can see how the erosions looks like. In this case, we can select a smooth fill. So we can compare these results with your results without the swirler to see what is the difference, to access actually how effective is the swirler. And now this result that we're seeing is the erosion that is plotting along this line. And we can change also here as in terms of angular theta. So what we can do is we can go to your XY and change this one to scalar. And select the functions for scalar. It could be the positions that we just created, the spherical coordinate we just created, and using data here, so we can see now the positions is outputted in the format of data, okay, in angular formats. So this representing how the erosion looks like along this line. And definitely we can see the impact of the swirler, especially in these regions. Compare with the literature's versions. This is the literature versions. We definitely can see the impact over here. What's normally to be a full erosions, and now because of the swirlers and the floors around this band is being affected by the swirlers, but pushed away. The floors here at the band is being pushed away, okay, from the wall by the floor from the swirlers. So there's the incoming floors here try to absorb the impacts of the floor at the band here. So obviously you can change the positions of the swirler and change the size of the swirler as well as the angle to find actually the optimal configurations or orientation that can reduce the erosions in this region the most. So that will be all for today. So good luck in your CAD simulations. Thank you.